OMMUNICATIONSYSTEMSLABCOMMUNICATIONSYSTEMSLAB. Experiment 0.2 Second-order active filters. Objectives: to understand the basics of active filters, to analyze the behavior of second-order active low-pass filter practically, to analyze the behavior of second-order active high-pass filter practically. Equipment required: DMM oscilloscope function generator, DC power supply, plus 12 volts fixed, minus 12 volts fixed, resistors 10k omega, QTY equals 1, 1k omega, QTY equals 1, 330 omega, QTY equals 2, 100 omega, QTY equals 2, capacitors, 0.01 UF, QTY equals 2, IC, op-amp, LM741, QTY equals 1, connecting wires. Theory: a filter is a frequency selective circuit that passes certain frequencies and attenuates all other frequencies. The pass band of a filter is the range of frequencies which is allowed to pass through the filter. The cutoff frequency, critical frequency, is normally specified at the point where the filter's response drops to 70.7% off its maximum value. Filters may be classified in a number of ways: A. Analog or digital filter. C. Passive or active filter. Z. Audio frequency, AF, or radio frequency, RF filters. Analog filters are designed to process analog signals. Digital filters process analog signals using digital techniques. Passive filters consist of resistors, capacitors, and inductors. Active filters employ transistor or op-amps in addition to the resistors and capacitors to provide voltage amplification and signal isolation. The high input impedance of the op-amp prevents excessive loading of the driving source, and the low output impedance of the op-amp prevents the filter from being affected by the load. The type of LA Mentor dictates the operating frequency range of a filter. For example, RC filters are commonly used for audio or low-frequency operation, whereas L-core crystal filters are employed at R for high frequencies, especially because of their high Q value. Figure of merit: the crystals provide more raise-table operation at higher frequencies. In the audio frequencies, inductors are of 10 not used because they are very large, costly, dissipate more power and emit magnetic fields. Part 1. Second-order active low-pass filter. A filter that provides a constant output from DC up to a cutoff frequency, FL, and then passes no signal above that frequency, FL, is known as an ideal low-pass filter. A first-order active low-pass filter provides the practical slope of minus 20 decibels decade, whereas a second-order active low-pass filter provides the slope of minus 40 decibels decade. Cutoff frequency, FL, is the frequency at which the voltage gain is 70.7% off its maximum value. Figure 2.1 shows the second-order active low-pass filter. It can be seen that two first-order low-pass filters are cascaded together to form a second-order two-pole. The op-amp fast-beam connector DAS a non-inverting amplifier. The closed-loop voltage gain of this non-inverting amplifier can be adjusted by varying RF and Re. The cutoff frequency, FL, of low-pass filter is determined as FL equals Hulp-Walkboy 2.1, where R1 equals R2 equals R and C1 equals C2 equals C. Procedure: A. For the circuit of Figure 2.1, calculate and record the cutoff frequency of second low-pass filter using equation 2.1. Figure 2.1, second-order active low-pass filter. FL, calculated, equals B. Construct a circuit of Figure 2.1 on the breadboard. Apply an input signal V. Sig equals 50 mV. pp. Vary the signal frequency, FSIG, from 50 Hz to 1 MHz. Measure and record their output voltage in Table 2.1.FILLTHETABLE 2.1 AS required. Table 2.1 Output Input Senior Voltage Frequency No. A equals P V KFDB equals 20 log P FSIG VO 150 Hz 2100 Hz 3200 Hz 4400 Hz 5600 Hz 6800 Hz 71 kHz 83 kHz 95 kHz 1010 kHz 1120 kHz 1230 kHz 1348.25 kHz 1460 kHz 1570 kHz 1680 kHz 17100 kHz 18200 kHz 19400 kHz 20600 kHz 21800 kHz 22.1 MHz C. Draw gain, AF versus frequency, FSIG, curve on the graph paper given in Figure 2.2. Figure 2.2 Gain frequency curve for the second-order active low-pass filter. D. Obtain the value or cutoff frequency from the gain frequency curve ACE plotted above. FL measured equals E. Compare the calculated and measured value of cutoff frequency, FL. Part 2 Second-order active high-pass filter. A filter which passes signals above a cutoff frequency, FH, known as high-pass filter. An ideal high-pass filter significantly attenuates or rejects all frequencies below their cutoff frequency. A first-order active high-pass filter provides the practical slope of plus 20 dB decade, whereas a second-order active high-pass filter provides the slope of plus 40 dB decade. Cutoff frequency, FH, the frequency at which the voltage gain is 70.7% of ITS maximum value. Figure 2.3 shows the second-order active high-pass filter. It can be seen that two first-order high-pass filters are cascaded together to form a second-order, two-pole, the op-amp fast-beam connected as a non-inverting amplifier. Their closed-loop voltage gain of this non-inverting amplifier can be adjusted by varying RF and RE, the cutoff frequency. FH of high-pass filter is determined as FH equals Hultboy 2.2, where R1 equals R2 equals R and C1 equals C2 equals C. Procedure A. Fourth E-circuit or Figure 2.3. Calculate the cutoff frequency of high-pass filter using equation 2.2. Figure 2.3 Second-order active high-pass filter. FH calculated equals B. Construct a circuit of Figure 2.3 on the breadboard. Apply an input signal Vsig equals 50 mV pp. Vary the signal frequency, FSIG, from 50 Hz to 1 MHz. Measure and record the output voltage in Table 2.2.FILLTHETABLE 2.2 AS required. Table 2.2 Output Input Senior Voltage Frequency No. A equals P V KFDB equals 20 log P FSIG VO 150 Hz 2100 Hz 3300 Hz 4500 Hz 5700 Hz 61 kHz 72 kHz 85 kHz 910 kHz 1030 kHz 1160 kHz, 12,100 kHz, 13,150 kHz, 14,159.23 kHz, 15,170 kHz, 16,180 kHz, 17,200 kHz, 18,300 kHz, 19,500 kHz, 20,700 kHz, 21,900